Hello, welcome to this video. So this video is going to be slightly unusual in that, yes, this is a continuation of the introduction to quantum field theory, where I'm going through the book Quantum Field Theory for the Gifted Amateur. However, this video will be really a discussion of how we can get to particles which almost create particles, which we do by using operators called creation and annihilation operators. But we're going to be developing them as they are seen in non-relativistic quantum mechanics, in which they can only really generate pseudo-particles like phonons, where they don't generate particles in the standard model, but they do cause particle-like phenomena to occur by quantization. And this kind of idea will be very useful in quantum field theory, though we will have to adapt it a bit, because in quantum field theory we're talking about the creation and annihilation of real particles, not pseudo-particles. And also, in this video, this hasn't really been scripted much at all. I've mainly put in the core equations we need to discuss, and I'll be just discussing, so this will perhaps sound a little bit like me rambling, but hopefully it's useful rambling at least. So welcome to this video, and today we're going to be talking about how to create pseudo-particles using operators in non-relativistic quantum mechanics, which will be a good bridge to how we create particles in quantum field theory. So we're going to eventually get something called a number operator. And to get to this, we introduce the Hamiltonian for simple harmonic oscillator, which is kind of like the quantum analog of a mass oscillating on a spring, or the quantum analog of the motion of a pendulum when it's displaced by a small angle. So we see simple harmonic motion in classical physics, but there's also a quantum version. But as is the case with quantum mechanics, we replace the physical observable energy with an operator called the Hamiltonian. And the Hamiltonian for the simple harmonic oscillator in quantum mechanics is given here. And one neat thing about this is this Hamiltonian causes the energy levels to become quantized in such a way that the energy levels form equally spaced steps in a ladder almost. And so we can think of a particle going from one step in the ladder to the next as going up in energy level, or we can think of this motion as the particle absorbing a particle with energy equal to the difference in energy levels between where it began and where it ended up. And in this way we get kind of like pseudo-particles, like phonons and stuff. But we can write the Hamiltonian in this form, where you can work out what A, dagger, and A are in terms of momentum and position operators using these two equations, and the book goes into a fair bit of detail on it. But for our purposes, it's worth saying that A is an annihilation operator, so it's like removing a particle of energy from our system, and A dagger is a creation operator. It's like putting a particle of energy into our system. And an important relationship which holds with the creation and annihilation operators we use in quantum field theory, which are like abstractions of these operators here, because strictly the operators I'm talking about at the moment are ladder operators, not creation and annihilation operators. But the abstraction of what we're doing here is creation and annihilation operators. And what even here A does is A removes a particle of energy from our system, so we can think of it as essentially destroying particles of energy, whereas A dagger creates a particle of energy in our system, so we can think of it as causing particles of energy to come into existence. But importantly, these particles are pseudo-particles because we're not using the abstraction of the ladder operators here. But we're using the abstraction as we will in future videos on quantum field theory. We will see how lots of ideas apply, including the fact that the bottom equation, this commutation relation, still holds even in the case of the abstraction. And it's a very important relationship. And if we want to know how many particles of energy we have in our system on which we have caused particles to be excited above the ground state, then we use something called a number operator, which is n, which we can get by multiplying a dagger with a. And we can then write the Hamiltonian explicitly in terms of the number operator, which is useful if we want to know how many particles we've added or taken away from our system. So, in summary, n tells us the energy the system has reached above the ground state. Hello, so I'm going to show essentially how we can generalise what we've looked at to look at harmonic oscillators when we have a number of them which are uncoupled, which means we have harmonic oscillators which are interacting with each other, which will be very useful when we look at quantum field theory. So we start with the note that using what I have already shown, although I'm not doing it explicitly here, one can actually derive exactly how A acts on our quantum states, and we can see that A hat does indeed diminish the energy of our quantum state and therefore acts as an annihilation operator, whereas A dagger increases the energy of our state. And repeatedly using A dagger, one can show, and this is fairly straightforward if you're familiar with factorials, that we can construct a state with any energy starting from our ground state, where our ground state is represented as the zero around, well, inside the ket. We can get any energy state we like by acting on the ground state many times with our creation operator, and then due to normalization we have to then divide by the square root of n factorial, where n is the number of times we've acted on our ground state to get to the nth excited energy level. So now, as promised, we're going to look at non-interacting harmonic oscillators, where the kth harmonic oscillator has a Hamiltonian hk, and to get the overall Hamiltonian we just sum over our oscillators. And because the oscillators are independent, it's fairly clear that because I and J are independent oscillators, that A, Y, A, J in a commutator would equal 0. And if we're looking at the creation and annihilation operators, the commutator will equal 0 if we're talking about different oscillators, but if we're talking about the same oscillator, then the commutation we had from the previous slide holds, and it will have to equal 1, thus we get that A hat I, A hat dagger k must equal the delta function. Sorry, not the delta function, the Dirac. Well, it's kind of a function, so it's really the Cranach delta symbol. But anyway, that's this video. If you like this video, please check out my other videos, but hopefully see you more soon.